Welcome to lesson 2.6, Pre-Calculus, solving nonlinear inequalities. In this lesson, day 1, we're going to learn to solve polynomial inequalities. Unlike linear inequalities where we graphed the line and shaded the solution set, with nonlinear inequalities, we actually are going to describe this now that we're in pre-calc on intervals and interval notation. For which intervals of the domain is the function either greater than or equal to 0 or greater than 0 or less than or equal to 0 or less than 0. So we're asking, when we ask these questions, we're asking when is the graph, here's f of x, where is, over which intervals is the graph or the output either on the x-axis or below the x-axis. For this one, for which ones is it strictly below the x-axis but not on the x-axis? For this one, for f of x, for where is it greater than or equal to 0, where is it on the x-axis and above the x-axis? And when it's strictly greater than 0, the function, where is it strictly above the x-axis? So that's what we're looking on, describing those intervals. Polynomial inequalities can be solved by making a sign chart after we get the inequality equal to 0. So we're going to get the inequality equal to 0 and we're going to make a sign chart. That sign chart will help us determine where those values are true. Where is the overall function if we put everything on one side greater than or equal to 0 or strictly less than 0 or strictly greater than 0 or less than or equal to 0. A sign chart is something that we make. It's a number line. It's a number line where we place the zeros, and when we get to tomorrow's lesson, solving rational inequalities, any interruptions in the domain, and consider intervals of the domain where the function is greater than or equal to 0. Okay, so looking at this graph right here, I have a 0 at -1, 2, 3, 4, and a 0 at -2, and a 0 at 2, and a 0 at 5. So a number line was made for where those zeros were. Okay, and I'm making a note. Now I'm doing this based on the graph, but we'll probably do ours based on a table, because we could plug, if we knew what the function is, we could plug in -5 into the function, we would get a positive output. So we know that to the left of -4, the graph is above the x-axis. And then we also know that between -4 and -2, we can see that it goes below the x-axis, but we could plug in a number like -3 between those two zeros to find that sign value. We don't care about the actual output, just whether it's positive or negative. That's why this is called a sign chart. What's the sign? Is it positive or negative? Between -2 and 2, all outputs are positive. Between 2 and 5, all outputs are negative, and to the right of 5, all outputs are negative. So I've had people in the past who thought, oh, once I find one of them, I can just alternate the signs. But as you can see here, there's multiplicity at, or even multiplicity at x equals 5. Maybe it's multiplicity of 2 or 4 or 6, we're not sure. But we do know that because of that, it bounces there. So this side of 5 is negative and this side of 5 is negative. So we can't just assume that these signs are going to alternate once we find one of them. We actually need to find the signs for each interval between our zeros and our domain interruptions when we get to rational inequalities. Solving each inequality, we'll start with this example right here. X squared minus 6x minus 30 is greater than or equal to -3. With this function, right now it's not greater than 0, so we're going to add 3 to both sides, giving us x squared minus 6x minus 27 is greater than 0. We're looking at this function f of x and seeing where is it greater than 0. So I am not at all, I do not want to answer where my x-intercepts are. Okay, I need to know where my x-intercepts are for my sine chart, but I don't want the answer to include that because the x-axis should not be included unless there's an equality bar. When it's not, I just want to know where it's above or below. In this case, I want to know where the graph is above the x-axis. So I'm going to factor first to try to find my zeros. If I can't do that, I'll do quadratic formula. X minus 9 by x plus 3 works when I set it equal to 0. So my zeros are x equals 9 and x equals negative 3. But I'm not interested in solving the quadratic. I'm interested in solving the quadratic inequality. So on my sine chart, I'll put 9 and negative 3. I have to then put this function into the graphing calculator. So I'm going to put in, for y equals, I'm going to put in x squared minus 6x minus 27, and I'm going to go to my table. I know negative 3 is a 0, I know 9 is a 0. I need to test values to the left of negative 3, so I'll put in negative 4. Since I got positive 13, I know that all the outputs on this side are positive on the left of negative 3. Between negative 3 and 9, I'll go with 5, but I could pick any number. Those signs are negative. They're below the x-axis. And to the right of 9, they're positive again. So this one, I'm assuming if I graph it that I'm not going to see a bounce. I'm going to see actual x-intercepts where it crosses crosses the x-axis. I have signs here, so I can determine where it's positive, where it's negative. This inequality says they want to know where the function is greater than 0. Well, that's where the signs are positive. So everything to the left of negative 3. So this statement is true over the following domain interval. From negative infinity up to negative 3. At negative 3, we're not going to include that with a bracket because it doesn't have equality. So I'm putting an open circle here because I don't want to include that in my answer because it doesn't have equality. So negative infinity up to negative 3, and then the graph is also positive from 9, not including 9, and everything to the right. So there's the domain interval for which this graph is solved. We have now solved this inequality. This inequality here is greater than negative 3 when this inequality is greater than 0, and that happens on these intervals for the values of x that will make this inequality true. If this were less than negative 3, then I'd be looking at this being less than 0, and then I would have picked the interval between negative 3 and 9, again with parentheses, not brackets. The only way I would put brackets on is if I had closed circles on my sine chart because this had an equality bar. Let's take a look at letter B. They want to know when this function is less than 20. Well, to solve that, I'm going to subtract 20 from both sides to get it the function equal to 0. So I have x squared plus 5x minus 14 is less than 0. In factoring this, if I have positive 7 and negative 2, that means my actual zeros that are going to go on my sine chart are negative 7 and positive 2. Because it does not have equality, I'm going to put open circles on that on my sine chart so that I use parentheses and not brackets when I do my domain intervals. I know that this graph opens up, and since it's a quadratic, I kind of already know what happens. It's going to open up from here, and it's going to be negative here. But maybe I didn't know that going in. So I'm going to show you how to do the sine chart because some of our functions won't be that obvious. So we have x squared plus 5x minus 14. Put in the graphing calculator. I put in negative 7 and 2 to verify that they're zeros. I put in negative 8, 1, and 3. And sure enough, to the left of negative 7 is below the x-axis, or above the x-axis, because it's positive output. Between negative 7 and 2 is a negative sign. All of those will be below the x-axis. And to the right of 2, all of those are above. Once again, they alternated. This time, however, I'm asked to solve for when the function is less than 20 or in other words, when this function is less than 0. That happens between the x value of -7 and the x value of 2. So my interval notation is from -7 to 2. Now we also know the end behavior. So if I asked you to describe the end behavior, you look at the signs at the ends. This is a polynomial function. It doesn't have any horizontal asymptotes or slant asymptotes like rational functions do that could change the end behavior or have an impact on the end behavior. So we know that it's just going to follow the sign. The limit as we go to the left on f of x. As I go to the left, the outputs will continue to be positive. So they will go toward positive infinity because this is a quadratic and even degree polynomial. The same is true as I go to the right. It will be positive infinity. You may also be asked for the limit to describe the end behavior. So this is end behavior. This is just making our sign chart, which is part of our evidence to solve the inequality. This is our answer for the inequality. I'm going to take a look at letter C. In this example, we have a cubic function, and lucky for us, it's already less than or equal to 0. If it wasn't, I would get it less than or equal to 0, or get it set up with respect to 0 so that I could put it in the calculator. I have 3x cubed minus 4x squared minus 13x minus 6. And I'd like to find a 0 so I can find the zeros. One of the zeros is 3. Hey, lucky me, I had that in the calculator. But I could look at the graph, or I could do rational roots theorem and find a 0 to get it down to a quadratic. One of them is 3. It looks like the other one's -1. So if I can get them just from this, since I'm not asked to formally solve the actual equation, yay for me. So I have zeros at -1 and at 3. If I couldn't get them this way, then I'd go through what we did in 2.5 with the rational root theorem, or actually 2.4 with the rational root theorem, dividing it down to a quadratic, finding all 3 zeros. The reason I only have 2 on my number line is this one has multiplicity of 2. And we can see that on the graph by the bounce. So I now know that those are my zeros. This does have equality because of the equals bar. I'm going to put in solid circles. They will be part of my solution. So I'm going to use brackets when I describe the interval for which this function is less than or equal to 0. In other words, where it's below or on the x-axis. I'm going to plug in values to the left of -1. I know we could just look at the graph, but we're supposed to do it this way. So I'm going to plug in values to the left of -1, and I get negative outputs. Between -1 and 3, so I'll pick 2, is also negative outputs. To the right of 3 is positive outputs. Notice on this one our signs did not alternate because of the multiplicity of 2, because of the bounce. To the left and right of the 0, x equals -1, the graph is going down. To the right of that 0, x equals 3, the graph is going up. They want to know when this function is less than or equal to 0. Well, that would be on this entire interval. It would include this, so I don't need to separate that interval. If this were an open circle, I'd have to do -infinity up to here, and between this and this. But because it's a closed circle, it's from -infinity all the way up to and including 3, because those are actual zeros. That's where it's equal to 0. So -infinity up to positive 3 and including positive 3. Had it been strictly less than, then it would look very different. It would be -infinity to -1, not including it if it was strictly less than, joined with -1 to positive 3. That's if it had been strictly less than 0. But for this problem as it's written, this is our solution. Now in terms of our end behavior, again, it's a polynomial function. To the left, it's an odd degree, so it functions like a line. We expect it to have, right? We know how to describe end behavior for these. So I'm not going to talk about that, but you can look at the sign chart too, as long as it's polynomial. If it's rational, you got to be careful of those asymptotes. Letter D. We have another quadratic. Let's take a look at this one. We've got x squared plus 2x plus 5 already equal to 0, or greater than 0. This one is also not factorial, so I'm going to do quadratic formula to solve it. Opposite of 2 over 2 plus or minus the square root of 4 minus, 4 minus a, or 4 minus 4 times a times c is negative 16, also over 2 times 1. So the x-intercepts are negative 1 plus or minus, plus or minus 4i over 2, which is 2i. That means I have no real x-intercepts. What does that mean? Well, in terms of our graph, and I haven't hit the graph and calculator, this is a positive lead coefficient. We know it opens up. Well, it's not supposed to touch the x-axis then, because there are no real x-intercepts. So this must be opening above the x-axis. And in fact, it is. So when they say, where is this function of greater than or equal to 0? Not even greater. Is it just, where is it strictly greater than 0? It is greater than 0 for all values of its domain. So from negative infinity to positive infinity, never does it equal 0. It never touches the x-axis, and never does it drop below it. So for every x value that you could come up with from negative infinity to positive infinity, you plug it in, you're going to get a positive output for this function. Now, had that said x squared plus 2x plus 5 is less than 0, where is that? It doesn't exist. So that inequality would have no solution. Let's take a look at letter E. We have x squared plus 5x plus 8. I could do the quadratic formula to solve it if I needed to. And oh, look at that. It does say less than 0. Well, there are no zeros, so the entire time this has positive outputs. So it will never be less than 0. So it is no solution. This concludes the video for solving for solving polynomial inequalities. You do need to get the equation to 0 on one side and then make a sign chart before you determine the intervals for which the inequality is true. In the next day's clip, we will be looking at solving rational inequalities. Have a great day.